Good afternoon. Today let us see the problems again. So these are the exercise problems that are given in the R.K. Bansal Strength of Metal Spokes. Thanks to the author R.K. Bansal. Determine the value of Young's modulus and Poisson's ratio of a metallic bar of length 25 centimeter, breadth 3 centimeter, and depth 2 centimeter when the bar is subjected to an axial compressive load of 240 kilonewton. The decrease in length is given as 0.05 centimeter and increase in breadth is 0.002 centimeter. So you can see uh, the dimensions are represented in the figure. Okay, the length, breadth, thickness, and it is subjected to an axial compressive load of 240 kilonewton. Okay, so these are the given data. Okay, so we have to find the Young's modulus and the Poisson's ratio. And Poisson's ratio is equal to lateral strain divided by linear strain or longitudinal strain. Okay, so Poisson's ratio is equal to lateral strain divided by linear strain. So delta L is available and L is also available. Delta B is available, B is available. We can calculate the Poisson's ratio, which is coming out to be 0.33. And the extension or elongation, whatever it is, or a decrease in length, whatever it is, delta L is equal to PL by AE. Okay, so all the data are available. You have to find E Young's modulus, which is coming out to be 2 into 10 power 5 Newton per millimeter square. Next problem. A steel bar 320 millimeter long, 40 millimeter wide, and 30 millimeter thick is subjected to a pull of 250 kilonewton in the direction of its length. Determine the change in volume. Take Young's modulus 2 into 10 power 5 Newton per mm square, and m is equal to 4, which is nothing but 1 by m. 1 by m is equal to 1 by 4. So Poisson's ratio is nothing but 0.25. Okay, so we need to understand. Okay, so in the diagram, they were represented all the dimensions. Okay, these are the given data. So we have to find delta V, the change in volume. The change in volume by original volume is nothing but the volumetric strain is equal to strain E into 1 minus 2 by m. 2 by m is nothing but 2 into 1 by m, where 1 by m is the Poisson's ratio. By taking this V to the right hand side, cross multiply it, you get delta V, the change in volume. Delta V is equal to E into 1 minus 2 by m into V. Okay, so stress is nothing but the load by area. Load is, I think by mistake, it is written 25. It is supposed to be 35, sorry, 25,000 only. Okay, the figure it is mentioned 35,000. Yeah, it is 25, 250 kilonewton, 250,000 by area, 40 into 30. Okay, so you get stress to be 208.33 Newton per mm square. And strain is stress by Young's modulus. Strain is stress by Young's modulus. So stress is available, Young's modulus is available. So strain is 1.0416 into 10 power minus 3. It has no unit. Okay, so strain is available. Substitute here. So to get the uh, change in volume is equal to strain into 1 minus 2 by m into volume. So the strain is 1.0416 into 10 power minus 3 into 1 minus 2 by m, that is 1 by m is 1 by 4, that is 0.25, into volume is length into breadth into thickness. So the change in volume is 199.98 mm cube. This is the answer. Okay, so here by mistake in the figure it is given 35,000 Newton, but it is 250,000 Newton or 250 kilonewton. Please make a note. So next problem, a metallic bar 250 mm by 80 mm by 30 mm is subjected to a force of 20 kilonewton tensile, 30 kilonewton tensile and 15 kilonewton tensile along x, y and z directions respectively. Determine the change in the volume of the block. Take Young's modulus 2 into 10 power 5 Newton per mm square and Poisson's ratio 0.25. So you can see it is represented in the figure. Okay, sigma x, sigma y, sigma z are the stresses, or you can write px, py, pz are the forces in the respective x, y, and z directions. So you know that volumetric strain delta V by V formula, sigma x plus sigma y plus sigma z divided by E into 1 minus 2 by m. Okay, and volumetric change in volume is given by, you just take this V to the right hand side, numerator. So this is the expression to find out the change in volume. Okay, so these are the dimensions: length 250 mm and breadth is 80 mm and thickness is 30 mm. So loads in the respective x, y, z directions are given here. Px 20 kilonewton tensile, Py 30 kilonewton tensile, and Pz is 15 kilonewton tensile. So stress in x direction is equal to load in x direction divided by the normal surface area. This is the normal area, normal surface to px load. So that area we have to take. Okay, stress force divided by that surface area which is normal to the application of the force. That area we have to take. So force divided by 80 into 30 gives you the stress in x direction 8.33 Newton per mm square. And the stress in y direction, load in y direction is Py 30 kilonewton divided by the area. So this area 250 into 30. So you get stress to be in y direction as 4 Newton per mm square. And the stress in z direction is equal to load in z direction is 15,000 Newton divided by this area. Okay, so 250 into 80 is a normal surface. So you get 0.75 Newton per mm square. So the change in volume is equal to substitute sigma x, sigma y, sigma z and E value, and 1 by m Poisson's ratio is 0.25, and volume is length into breadth and thickness. So 250 into 80 into 30. So you get the change in volume delta V is coming out to be 19.62 mm cube. So now let us go to the next problem. A metallic bar 250 mm by 100 mm by 50 mm is loaded as shown in figure. Find the change in volume. Take Young's modulus 2 to 10 power 5 Newton per mm square and Poisson's ratio 0.25. Okay, this is the first part of the question. Second part, also find the change that should be made in the 4 meganewton load in order that there should be no change in the volume of the bar. I'll come to the second part later. Now let us start doing the first part, find the change in volume for the given loading. Now we have seen in the previous problem all the three forces are under tensile. Now here the force which is acting in the z direction is coming out to be compression. So we have to represent the stress value in the expression as negative. So this is the volumetric strain formula Ex plus Ey plus Ez. This we have seen in the last week class. So delta V is equal to Ex plus Ey plus Ez into V. So this is the basic strain, direct strain expression when all the three forces under tension. Now here in this case, the force acting in z direction is negative. So this plus z will change to minus z. You can see here plus z is changed to minus z, and plus sigma z is changed to minus sigma z. Now this is the expression which is valid for the given problem, and this is the expression which is valid for the block which is subjected to three mutually perpendicular forces that are that all the three forces are under tension. Okay, so this is the volumetric strain when all the three forces are under tension. Okay, so now sigma z is compression. So here minus sigma z, here minus sigma z. You can see here minus sigma z, minus sigma z. So sigma x plus sigma y minus sigma z is common. So we have taken outside into 1 minus 2 by m. So delta B change in volume is equal to sigma x plus sigma y minus sigma z divided by E into 1 minus 2 by m into B. And we can calculate as I explained in the previous problem the load acting in x direction divided by the normal surface area. Okay, so you know the px. Okay, this is px and this is py and this is pz. Okay, please remember the force values. And for px, 100 into 50 is the area, and for py, 250 into 50 is the area, and pz, 250 into 100 is the area. That's a normal surface for all the three loads. Okay. So with this as input, we are getting the sigma x is equal to 80 Newton per mm square, and sigma y as 160 Newton per mm square, and sigma z also 160 Newton per mm square. And you just plug in all the values here. Okay, all the values here. Okay, substitutes Poisson's ratio, and the volume is length into breadth into thickness. We are getting change in volume to be 250 mm cube. Now the second part of the question says that there should be find the change that should be made in 4 meganewton load in order that there should be no change in the volume of the bar, which means that there is no change in volume at all. So volumetric strain is zero, it says. So This is the expression. So we are just saying delta B by V is equal to 0. So what will happen? Well, you just cross multiply it. Okay, so this term will get vanished. Sigma x plus sigma y minus sigma z is equal to 0. So we have already calculated, and sigma z is nothing but Pz by normal area. Okay, Pz is a load acting in z direction. That load only we have to calculate now. So Pz divided by normal surface area is 250 into 100. So Pz is nothing but 6 meganewton. 6 meganewton is a load that must be applied on that, so that there won't be any change in volume of the bar. So next problem, a steel rod 4 meter long and a 20 millimeter diameter is subjected to an axial tensile load of 40 kilonewton. Determine the change in length, diameter and volume of the rod. Take Young's modulus 2 to 10 power 5 Newton per mm square and Poisson's ratio 0.25. So I have represented in a figure, okay, 40,000, 40,000, 4,000 mm length and 20 millimeter diameter. So these are the given data. So delta L is equal to PL by A. Okay, P is the force, 40,000 Newton, and length is 4,000. Area is pi by 4 d square, and E is 2 to 10 power 5. You get 2.546 millimeter. Delta L by L is nothing but the strain, which is coming out to be 6.366 into 10 power minus 4. Poisson's ratio, lateral strain divided by linear strain. So Poisson's ratio is given 0.25. Delta L by L is available. D is available. You have to find delta D, which is coming out to be 3.183 into 10 power minus 3 millimeter. So we know the volumetric strain, that is delta V by V is equal to E into 1 minus 2 by M. So delta V is equal to, take V to the right hand side, substitute the value for the strain and substitute the value for Poisson's ratio 1 by m 0.25. Volume is pi by 4 d square into length. So the change in volume is 399.98 mm cube. Thank you.